welcome to the channel. It's W3 here. In today's Python tutorial video we're going to be learning about memoization and more specifically the LRU cache. So if you haven't already, hit that subscribe button so you don't miss out on more great content in the future. So we're going to go over memoization quickly just to show you how easy it is to sort of implement a cache and how easy it is to optimize your code, etc. So first of all we're going to import time, and then we're going to create an expensive function called memoization, and then we're going to have the parameter num. We're going to print computing ... and then we're going to do the result, which will equal num times num. That's going to be our result, which we're going to return result. Now to make it an expensive function, something that's using hardware, taking its time, etc., we're going to do time.sleep, and we're going to give it 2 seconds. Now we're going to run this code and we're going to see how long it takes, etc. With parameter of 4, we're going to run this 4 times and you're going to see it computing each and every time, even though there's no need to. You know, if we were using memoization now, or LRU cache, or any type of cache, it would be a lot better. Finished in 9.9 seconds. Right, so we're going to add a few lines of code and we're going to see a dramatic difference. Cache equals dictionary, and we'll do if num in cache, return cache, and then none. Put the key, and we're going to print cached. There we go. So we know it's been cached. And after the result, once it's computed, we're going to add it to the cache. So cache num equals the result. We're going to run it a second time, computing, and then we've got cached 1616. Finished in 2.6 seconds. So as you can see, this code has been optimized just from a little bit of code. So the LRU cache is going to be a lot more interesting and a lot more in depth, but that's just to give you an idea of memoization, caching, and what this video is about. So for the LRU cache, we're going to be using doubly linked list, and that will be for the order of the cache results, and that will have a head and a tail, and each node object will have a key and value pair, which will be in a tuple, and it will have a next and a previous. And in the LRU cache, as you can see, last item used in the list will be at the bottom towards the head, and when an item is added to the LRU cache, it will go to the top, tail, or if an item is called from the cache, that will get moved to the top of the cache, or doubly linked list. So to begin with, for the LRU cache, we're going to create a class called node, and that's going to be used for our doubly linked list. And our init method, and then self, which is referring to the instance of the class, and then our parameters are going to be key and value, and that's because the dictionary uses key and value. So our node is going to have the key and value pairs in a tuple. Self.key equals key, self.value equals val, and then we're also going to have a next and a previous, and that's so each node can link to the other node and therefore create a doubly linked list, going up the list to the tail and down the list to the head. Self.next equals none, self.previous equals none, and that will help also for inserting, adding a node into the list and removing a node from the list. Now it's over to the LRU cache, and we're going to create a class called LRU cache, and we're going to need to create an init method, which will initialize once we create an instance or an object of the class LRU. And then we're going to have self, which is referring to the instance of this class, and func. Now it's the same sort of idea as a constructor. The init method is going to take in the func function, and we're going to have a call method later on which is going to take in the arguments for the function. So self.func equals func, and then we need the cache, so self.cache equals dictionary, and then we need a head and a tail for our doubly linked list. So self.head equals node 0 0, and self.tail equals node 0 0. Now the reason we're using nodes and 0 0 is because then we've got two definitive points. We've got the bottom and the top, we've got the head and the tail, instead of using none, which some people do. Can get a little bit more confusing, a little bit harder to do, because obviously the node object, next and previous, they each have a none. So it's easier to know that we're at the top and the bottom once it hits node 0 0. By doing it this way, it's a lot easier, I feel. And then we need self.head.next to equal self.tail. So the bottom.next equals tail, yet, and then we need the top of the linked list. We need to link that to the bottom of the list. So self.tail, which is the top, dot previous equals self.head. So now we've created a doubly linked list. Both nodes are linked together, head and tail, next and previous. Now we're also going to add a class attribute, which is going to be the cache limit, and we're going to just put that to 3 for now, just for the sakes of this video. Obviously in real life you'd have that depending on what your cache is used for and what sort of limit you need. Now it's time for the call method. So we're going to do def underscore underscore call underscore underscore, and self again referring to the instance, and we're going to take in the args and the quarks. Also, just like in memoization that I showed you earlier, we're going to do if args in self.cache return, and then f format, and then we're going to do cache dot 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 curly braces self.cache square brackets args, and that will fetch the key from, that will fetch the results from the cache and return them. And also before that, we're going to need to, if they're in the cache, we're going to need to go into the doubly linked list, and we're going to need to move the key and value pair tuple to the top of the list because it's been called. And if it hasn't been called, it will slowly go down the list, and then eventually it will be deleted, removed. So we're going to do self.ll ist, and that's referring to linked list, and then we're going to give it the parameters of args, and we'll do that function later. Also we're going to do if length of self.cache is equal to self.cache underscore limit, node equals self.head.next, and then we're going to do self.underscore remove node. Now we haven't created that function either, but we're going to do that in a little bit as well. So we've got L list to create, and we've got remove, and we're also going to have add to create, and then we'll just delete it from the cache. So delete self.cache node.key, because every node has got a key and a value. So yeah, node.key, we're deleting that from the cache. So now we need to compute the results of the function that is being used by LRU cache wrapper. So results equal self.func, and then we're going to put the args and the quarks in. And just like before in memoization, you need to add it to the cache after the results if it's not already cached. So self.cache args square brackets equals results, or should we say result. And then we need to create the node which will have the key and value pairs in, so we can put that in our linked list for the order of the cache. So node equals node, and then args and result, and then we need to add it to the doubly linked list. which we haven't got a function for yet, but we'll be creating that in a bit. So self._add and then node, and then we just need to return the result. If it's not been cached, just return the result after it's computed it all, etc. And that's that bit done. So the main bulk of the code, the call, that's been done. Now we just need to create the functions for adding a node, removing a node, and then we need to create the list function, which is for the linked list, which will add the nodes to the top of the list if they've been called and they're already in the linked list or in the cache, or removing the nodes as the cache limit gets reached. So now we need to make the remove function for the linked list. So we'll start off by def_remove self and the node that we want to get removed. Then we're going to do p equals node.previous. So p equals the node before this node here, and n equals node.next. So n equals the node after this one here. And then we're going to do p.next equals n, and n.previous equals p. So now we've got to make the add function, sort of similar, def_add self and the node that we wish to add. So we've got to go to the tail and then one below, so p previous equals self.tail, which is top of our linked list dot previous, and then p.next will equal our node, and then self.tail, which is the top, and then dot previous will equal our node. And then we just got to slot our node in by doing node.previous equals p, and node.next equals self.tail, as self.tail is the top of our linked list. And that's that. So now we need to create our linked list function. Here it is here, self.ll_list, and it takes in the parameters args, and that's so that if the arguments are in the cache, we move it from wherever it is in the linked list to the top below self.tail. So let's begin. Def ll_list, parameters self and args, and then current is going to equal self.head, that's the bottom of the linked list. Then we're going to do while true, and then if current.key is equal to args node equals current, and then we're going to add it to the linked list. Then we're going to remove it from the linked list, and then we're going to re-add it to the linked list. So self._remove the node. We remove the node from the linked list, whatever it may be. Maybe it's halfway down, but it's been used from the cache. It's been called again. So we're going to re-add it to the top. Add node. So we've added it back to the top of the list, and then break, and then else current equals current.next. Right, so now we need expensive function like we did in Memoization to run it and see how it works. So all that's next is we need to run the code. So I've already got two expensive functions here to run, just like in Memoization. You have to import time because they use time. Import time. Right, we're going to run the code, and here we go. Yep, it's computing, and it's cached and cached as well. Yeah, that's fine. And also here we can see that 4 is called, 4, yep, 5, 4, 5, 4 is called again from the cache, goes to the top, 7 is called at first, and 7 is called from the cache, and it's back to the top. That's it for this video, guys. I hope you've enjoyed it, and I hope you've learned something. Don't forget to hit that subscribe button for more future videos. I'll be doing some hacking tutorials on a hacking program, information gathering, so watch out for that, and goodbye.